Okay. The question is, how do you do multiple regression? So I'm going to go to the data for your homework 3, which is on the website. Yeah. And just plop in some stuff. Now there is a way to do x prime x. Okay. Unfortunately, I didn't have x exactly written down in this data. I'd have to permute the columns a little bit. This one column should be somewhere else, and then I think this I'm going to take as x1, and then I called it x6 instead of x2.
As long as isn't it just going to put out the betas in the order that you put them there, though? So like
yeah. You can do that, but if you want to keep track of everything, all right, you might have to permute the columns a little bit from this data set. Okay, how do you use the machine now instead of doing it by hand? Okay, because I'm showing you basically formulas for how to do it by hand on the board here to set up the theory. How would you do it with the machine? One way to do it is by hand, and I just go ahead and use the sum product, sum square formulas. So I think, in the for the 32, I just did the sum product of the ones with themselves. I just stuck it in there twice. Okay, I could use sum of squares. Here was the sum of squares of G5 to G36, which was the x1. This is the sum of squares of H5 to H36, which was the sum of xi6 squared. All right? I call it x6 rather than x2 because in the actual data set in the back of the book, that was the 6th regressor. Okay? This was the gasoline mileage data, and this was the engine size in cubic inches, and this must have been I don't know what this 4, 2, or 1 was. Has to do with some other thing in the engine. What? Yeah, one-cylinder car. That would be something. But anyway, maybe it was. It was some other kind of carburetor ports, or who knows what it was.
carburetor barrels.
Okay. And then I did, so on this one, for example, this is the sum of products of x1 and x6. Okay. So I could do it by hand if I had to, but there's an array formula. You have to look up how to do array formulas.
Oh, there's M mult too, which is a matrix mult.
Oh, that's what I wanted, M mult.
Yeah.
That's good. So how do you input a matrix?
I'll just go up and show
Yeah, just go ahead and show you how you input a matrix.
All right. So the easiest thing to do is actually define your matrix. So, for example, we want to call this vector, we'll call this one y. So now this vector's got a y. And I'm going to call this, I'm going to highlight the whole thing and call this x. Okay? Oh, escape. Sorry. Kind of put it
Escape is the key for getting out of anything, apparently.
So now this set is this matrix here is referred to as x. So if I do, I want to highlight, I know I'm going to result in a 3 by 3, so I have to highlight the 3 by 3 equals M mult of, what is it? What is the whole thing?
Prime, x prime.
Well, so the transpose of x, comma x, and I think it's Control-Shift-Enter, and that gives me x transpose.
Yeah, it's the same matrix, only in permuted things because because the columns were different.
So, but this, so that's the
Okay.
easy way to do it.
Shift Control Enter was the key for the array formula. So we had to the key was to highlight the 3 by 3 range before you start with your equal sign. See what I did? He named the things by going to the upper left. Did you see what he had on the upper left there?
I guess.
Maybe you couldn't see it. There's a formula bar, and there's also a little bar up here on the left. Can you see this little formula here? After he highlighted something, can you see that? The name box?
Yeah, it's there.
The name box. And he had an X and a Y in the name box. Okay? So he first highlighted some array, and then he gave it a name in the name box. That's great. And then, boy, this is really learning how to do it. And then, see how these have these special curly brackets around the array formula.
Yeah, I didn't have to type those. It kind of does that.
It does it by itself, but never try to edit an array formula. Or if you do, then use the escape button liberally, because it starts to like go crazy. All right?
And it tells you you're not allowed to change a single point.
You're not allowed to do anything once that baby is in there. So you can't start editing this highlighted region. Okay. So, but now if I wanted to, can I refer to that if I want to equal the inverse? So now can I highlight another thing?
Yeah.
3 by 3 and say equals. Whoops. I got
You have to click up in the cell up in the top bar there.
up here.
Equals MINV.
MINV, matrix inverse.
I believe, open parentheses, highlight your matrix.
The one I want?
Yeah. And then hit a close parentheses and hit Control Shift Enter.
Control Shift Enter. That's the key.
Okay, I did something wrong there.
Okay. So matrix inverse, maybe you need INVERSE.
You have to highlight the whole thing again. Just delete the whole thing and start over again.
Okay, so there's the problem. Escape. 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 I escaped it. Now how do I get rid of this thing?
Highlight the whole thing. You're allowed to delete it as a whole thing. And then you hit delete.
Delete. Phew. Okay, try it again. Up here. Equals.
M inverse.
M, you need the M. You didn't need the. You need matrix multiplication. You say M inverse.
Yeah, you're taking the inverse of that matrix, right?
Okay. Inverse of. Now highlight this.
Yep.
Okay. Close parentheses.
Yep. Control Shift Enter.
Control Shift Enter. So you can't make any mistakes. Ha! Beautiful.
What's with the whole Control Shift Enter?
That's how you establish the array formula.
Yeah, that's how it remembers to do it for all cells.
Control Shift. Yeah. So that's the super duper array formula. Array formulas are kind of a pain, but they exist. All right? So escape from this. Okay. So there's a way to do it. What about just, that's by hand. What about the actual calculations? Why don't I just try multiple regression, right? Regression, let's try that. So let's take data analysis and go to regression. Okay. And then input Y range, just go ahead and put this in. Input X range, put both X's.
You have to put in, you don't have to put in the constant?
No, because this is a with intercept. Okay, the default is with intercept. Okay, if you wanted to have no intercept, I could put constant as 0 at this point. Output range, let's just put it down here. Okay, and let's go ahead and get the residuals. Wherever you want to, output range is wherever you want it to be put out. Either you can put it on a new sheet or you can just name a cell where you want the upper left-hand corner of all the output to go. Okay, so there it is. Let's see what it gives you. It gives you the residuals. It gives you two betas, beta 1 hat, beta 2 hat. All right. It doesn't name the variables because we didn't name them. If we had named them, you know, fancy upper left-hand corner box and everything, we could have gotten this output a little bit nicer, I think. But since I'm weak in that area, I'm going to skip that. All right. They gave that there are two now degrees of freedom difference between residual. There are 2 degrees of freedom for regression. All right. There are 29 degrees of for the residual and 31 total. That's 32 minus 1. Because there were 32 data points in this problem. Okay. So there's the significance of the regression. It was already significant with 1 regressor, so it's certainly going to be significant with 2 regressors. The regression sum of squares is bigger than it is with just 1. I see that was which problem? 2.4 on your homework today. What was the regression sum of squares? It was 955.34. Now it's 974. Okay. Is beta 2 significant? Let's see. What's the t-statistic? No. P-value is only 0.16. I'm doing your problem right. Okay. So the way it also works is that, well, all right. I won't say anything more right at this point, I think. Again, you have these upper, this seems to be repeated here. There seems to be no value to these last two columns here. This seems to be a mistake in Excel. Okay? They gave you the same information twice. Maybe if they had set it up that way. Okay? Otherwise, I just clear it every time. Okay. Comments about this? All right, let's get the formulas for it. So actually, we could do it by hand as well. Okay? That would be a good exam problem, wouldn't it? No.
As long as the formulas are all in terms of the matrices and not actual numbers. I can remember that.
Okay. We need to have some formulas for how would we calculate the t-statistics, the standard errors, and all that good stuff. Okay. So we had stopped here about the H matrix. He calls this the projection matrix. This is what you find in linear algebra. This is the matrix that projects Y onto the column space of X. So you've seen that matrix before in linear algebra, I believe. Maybe unless your instructor didn't cover that section. So notice that if you project onto the column space of X, and then you've got something on the column space of X, and you project again, you don't go anywhere, right? Therefore, I shouldn't change the answer if I do it again. Therefore, H squared should equal H. Okay? So, indeed, H squared is equal to X prime X inverse X prime times X prime X inverse X prime. What happens? I can multiplication is associative, so I can put the X prime X here in the middle together. All right? This H is an n by n matrix. This is an n by n matrix. Because I'm taking something in Rn and bringing it back into Rn. Right? So I think what I was saying just after the hour ended last time was that you had the scatter plot of points. And you have this plane sitting here, the model for means in case of k equals 2 regressors. x1, x2, y. What you're doing is your prediction is you put all these dots onto the plane, right? But the vector y hat is then the vector of all those 25 points, 25 y values. Okay, 25 y values. Okay. So I'm taking a vector which is in 25 space, 25 long values of y, okay? And I'm constructing another vector, y hat, in 25 space. Okay, so I need an n by n matrix to do that transformation, and it is a linear transformation. And h squared, you can see this, x prime x, and that's the inverse of x prime x inverse, so you can cancel these. And so then you just simply get an h back again. All right, so that's the projection property. Okay. So what would be I'm going to get a corollary about H. What's the trace of H. Turns out I can calculate the trace of H. What's the trace of a matrix? This is an n by n matrix. What is it?
Just the sum of the diagonals.
Sum of the diagonal terms. What do you know? There's a very nice formula for the trace of a product. The trace of a product is the trace of a product A times B times C, okay, is equal to the trace of CAB, as long as all the products make sense, okay? Now what am I talking in this case? This is A, let's say, is an n by P matrix. Actually, he's going to make an abbreviation, P equals K plus 1 in this case, because that's the dimension of X. Can you read it?
I'm sorry, did you say sum of diagonals?
Sum of diagonal elements, yeah. So this is this equals summation HII. I goes from 1 to n, where H is equal to Hij, the little h's. Okay? Ij goes from 1 to n. I should call it HII prime probably because we already used j as the index between 0 and k, but pretend I didn't use the j already. All right, so the sum of diagonal elements. Suppose, so the formula is, as long as I can cyclically permute the factors. A, B, C, I can put the C back in front, then I can put the B back in front there, as long as all these products make sense in dimension-wise. So here, let's take the A equals X equals N by P. B is P by P, and C is P by N. So that makes sense. Then indeed, I can put the C in front, okay, and still make a matrix product. This is then P by N, A is N by P, and B is P by P. That makes sense, okay? As a product, it gives me a P by P matrix. So the trace of that matrix, the trace of that N by N matrix is the trace of this P by P matrix. It just follows by writing down the formulas for trace of a product, okay? I'm not going to go into that formula. It's just very convenient. Because now, if I plug that in this context with A equals X, B equals X prime X inverse, and C equals X prime, then I obtain the trace of, let's see, C was X prime, A was X, and B was X prime X inverse. Okay? Okay, equals the trace of I sub P. Okay? So that's equal to P. Kind of cute. Okay, equals K plus 1. All right, we're going to use that a little bit later. So what about the properties of the estimators? How are we going to calculate the standard error and so on and so forth? How are we going to actually know that the residual sum of squares, when properly normalized, is unbiased for sigma squared? All those things that we did in the simple linear regression case where we had a little bit more explicit formulas. Well, they seem more explicit. So what about properties of estimators? First, what do I mean? I talked about the expectation of a vector as the vector of expectations. Suppose now I let if A m by n is a matrix of real constants, then what is the expectation of AY? So here's m by n. So now I'm getting another column. I had a column of an n by 1 column of random variables. Now I'm going to get an m by 1 column of linear combinations of those random variables. And I take the expectation of that. That means, again, I take the expectation in each place. So that's the expectation of A11, Y1 plus A12, Y2 plus and so on plus A1n, Yn. That's one linear combination of the Y's. Then I get a second linear combination of the y's, a2, 1, y1, plus a2, 2, y2, plus and so on, plus a2, n, y, n. I'm assuming that the a equals a little aij, okay? I goes from 1 to m now. Maybe I should, again. So what happens, I'm just trying to make it as explicit as possible. If I multiply a random vector by a fixed matrix, then I get another vector of random variables, linear combinations to the original ones. am1 y1 plus amn yn. Okay. Now what I mean by the expectation is take expectation in each position. All right? Expectation of a vector is a vector of expectation. So this would be the expectation of a1 1 y1 plus and so on plus a1 n y1, and then so on down to expectation am1 y1 plus and so on plus amn yn. There should have been a yn there. So the column of expectations. Now the expectation of a linear combination is a linear combination of expectations. So what do you get out of this? Can you see the operations continuing?
A times the expected value of y.
Yeah, a times the expected value of y. So.
But that's just, the expected value of y is just what, beta x, or x beta?
Yeah, I can put that in. I just wanted to state this fact. Okay, so now if we go ahead and put in a equals let's see. Well, what am I going to apply that to? I guess I'm going to apply that to beta hat. Yeah, I'm going to apply that to y beta hat in place of y. So I'm going to apply this to expectation of beta hat. Therefore, equals expectation of x prime x inverse x prime y. So now the a is x prime x inverse x prime. So that becomes x prime x inverse x prime times y. Expected value of y is x beta. So then you simply get beta. So therefore, and that's beta in each component. So that's actually k equations. Oh, k plus 1. See, how is it? Yeah, it's actually k plus 1 equations. Real equations, because this is a vector equation. This is a vector equation. This is a k plus 1 by 1 equals k plus 1 by 1. It's saying that e beta 0 hat is equal to beta 0. It's saying that e beta 1 hat is equal to beta 1. It's saying e beta 2 hat is equal to beta 2, etc. So it's saying k plus 1 equations. Is that okay? So that means the vector beta hat is unbiased for the vector beta. So we have the unbiasedness. We can do it all in one equation instead of having to go through beta 0 hat, beta 1. We had to go through each one before. So this is already a savings. Now, what about the variance? That's the expectation. So you have unbiased estimators. And what about the variance of beta 0 hat, beta 1 hat, and so on? And what about the covariances between beta 0 hat, beta 1 hat, beta 0 hat, beta 2 hat, and so on, between beta j hat and beta l hat? All right, what are the covariances? Okay, there's another nice little result. All right. Okay, if w m by 1 equals w1 down to wm is a random vector, define the variance covariance matrix as follows, and you just do a capital COV of W. Okay? So now it's not just a real random variable, it's a vector of random variables, W1 through Wm, equal to just a matrix of covariances. Covariances between Wi and Wj. Ij goes from 1 to m. Okay, so it's going to be an m by m matrix. What do I mean by the covariance of Wi with Wj? Well, we defined that last time. It's an expectation of product. So covariance between Wi and Wj equals E of the shortcut formula. Well, it's E Wi minus mu I, Wj minus mu j. And there's a shortcut formula, E, the matrix, the expectation of the product minus the product of expectations. Okay, which simply is a variance if I put I equal to j. Covariance between Wi and Wi is the variance of Wi. That's usually how we write it. We never actually have to write variances if we allow just covariances. Okay, if we want to write a slightly longer notation. All right? So I call it the variance covariance matrix. We could just call it the covariance matrix as well. The diagonal elements are variances, which have to be non-negative. The off-diagonal elements don't have to be non-negative, but the diagonal has to be positive, actually, unless there's a trivial variable. Constant has zero variance. That's the only one that does. So this is only the m by m matrix. All right. So now, what's the covariance matrix of beta hat? That's the covariance matrix of A times Y for some matrix A, which we wrote down over there as x prime x inverse x prime. I want to just talk about this. How do you calculate the covariance of a matrix times a vector? Well, now that takes a little bit more computation. There's a formula for that. It's a nice little formula for that. What is it? Maybe you could guess what it would be. All right? Let's see, this is an m by n matrix, let's say, and this is n by 1. Let's see, so this is an m by 1 random vector, so it's got to be an m by m matrix in the end. Now, what do you know? You know that the variance of a constant times a random variable is the constant squared times the variance of the random variable, right? So we know this, that variance little a times W1 equals a squared times the variance of W1. So what would be the simplest formula that I would write out here in terms of capital A and the variance of Y itself, or variance covariance matrix of Y itself, such that I'd get an m by m matrix and would have the right scaling? What do you think? Well, that wouldn't be the right dimensions because A is not square. A is not square.
A transpose?
Yeah, there's a transpose. But where's the covariance of Y coming in?
Well, yeah, times the...
Okay, now get them the right order. Okay. A, covariance of Y, A transpose. Okay? This is m by n. This is n by n. This is n by m. So, and it has the right scaling and brings in the covariance of Y. That is the correct formula.
And that's where A is whatever we use.
X prime x inverse x prime. Yeah, I mean, you have to derive this formula, but this is a formula. This is an identity. So I'll just, you can go through this definition and do it. That's a good exercise. It is a good exercise. It takes a couple pages of just writing things down. And they say, oh, it was easy. Okay, now I have it memorized. Now I have a way to memorize it as well. Okay? Because it just follows, it has to be a generalization of this formula. Okay? And this definition. Okay? So, therefore, let's see. Then, yeah, so let's put in the x prime x. So put in x prime x inverse x prime. Covariance of y, the nice thing about that is sigma squared times the identity. Right? That's what we've assumed. Because we assumed the y's were uncorrelated or uncovariated. Covariance between epsilon I and epsilon j is 0. It means the covariance between yi and yj is 0 if I is unequal to j. So you get sigma squared times the identity there. And then you get x prime x inverse x prime primed. Okay? Now, x prime x is a symmetric matrix. Its inverse is also symmetric. So now I have to write the prime in reverse order. So I get x prime x inverse. I must have written this down a million times. X prime x inverse. I can pull the sigma squared out front. X prime, now I'll get an x, and then an x prime x inverse. Okay. So you get something that maybe you would have expected. This is sigma squared times x prime x inverse. And actually, you know what one of the entries is in that inverse matrix because we actually, in the simple linear regression case. Let's look at the simple linear regression case. Just make sure that that formula is correct. Let's recall simple linear regression. Where x prime x is equal to nx bar, nx bar, and nx squared bar. Okay, comes out. Okay, just because it was n summation xi, and summation xi squared. So x prime x inverse came out to be, they need to determine it 1 over n squared times x squared bar minus x bar squared, and then times you had nx squared bar and minus nx bar. I'm just trying to eliminate summation signs. That's why I'm doing the bar thing. I'm hoping it's not killing you. Okay. One of the ends will scale out, and so I'll get rid of one of the ends, and I get 1 over summation xi squared minus nx bar squared. I put the summation sign back in now, times I got rid of this end, so that's x squared bar. So this is 1 over n summation xi squared. This is minus x bar, and 1. Okay. Looks like I just did one of your grad problems, but anyway. Okay.
Yeah, but you didn't show any of the validations why to explain it. So
Okay, good. So what does this turn out to be? So if I now take, what does that mean? Okay, so now what I have is that the variance covariance matrix of beta 0 hat means the covariance matrix of beta 0 hat, beta 1 hat, is equal to variance of beta 0 hat, covariance between beta 0 hat and beta 1 hat, covariance between beta 0 hat and beta 1 hat. Now I'm almost doing the whole thing. And the variance between of beta 1 hat, okay. On the one hand, on the other hand, it's equal to this matrix, okay? Okay. So we actually have maybe a little bit simpler formula for the variance of beta 0 hat than we had before. I'm not sure if that's simpler or not.
It's about the same.
something divided by SXX. But it didn't look like, oh, I know, we didn't really do variance of beta 0 hat much before. We were talking about variance of a linear combination of beta 0 hat and beta 1 hat, namely the variance of the conditional, of the estimator of the prediction. Okay? So we were doing, so what we were actually doing was what's the variance of beta 0 hat plus beta 1 hat times x0. That we did have a formula for. This came out to be sigma, that came out to be, what happened to my, I'm sorry, that's sigma squared times 1 over n plus x0 minus x bar squared over SXX in this context, right? Simple linear regression. So you might ask, what? Okay, so I can now find the variance of beta 0 hat, the variance of beta 1, and therefore I can find the standard error, and so on and so forth, as long as I know what sigma hat squared is. Okay, so I have formulas in terms of this matrix, sigma squared x prime x inverse. So I can read off. This is a k plus 1 by k plus 1 matrix corresponding to the fact that there are k plus 1 estimators. All right? The 1, 1 entry would give me the right thing to multiply by sigma squared to give me the actual true, actual variance of beta 0 hat. Okay, so this gives you the 2 by 2 case. And here's the 3 by 3 and higher cases. All right? So what is, how do I'm going to use sigma hat squared for sigma squared, but what is the right sigma hat squared? So let's look at the residuals. That's the last thing I need to do. Oh man, we're almost out of time. We need to calculate the expectation of E prime squared. So E is simply going to be y minus y hat, okay, equals, I don't need the arrow on the arrow on these anymore, I hope, equals y minus hy equals I minus h times y. Okay. Where h was that four-way looking thing. X prime, x inverse, x prime. Now, therefore, the covariance of E, I'm going to reserve this, I'm going to keep this. Yeah, the covariance of E, that's a random variable too. It's I minus h times y. This is not the epsilons. This is the estimated errors. Okay? But that the square length of that is what we call SS residual. Okay? E squared is the inner product of the square length in Rn. Okay? That is equal to SS res. Remember we had that picture with the triangle and all that good stuff? You've got you've got the column space of X is what I'm calling a plane. It's a different plane than the plane we had before. This is a column space of X. Equals the linear span of 1, x1, always go back to this picture, xk. All right, and then you have y, this big hairy vector out in Rn, y, and then you project onto this column space. So again, this is not the same plane as that I drew for the in R3 when k was equal to 2. Because this is a plane in Rn. Okay? Right? It's a slightly different kind of plane. Okay? It has dimension k plus 1. Okay? In fact. All right? Dimension equals k plus 1. All right? So then you have this picture, and so this is y hat. Okay? And and then you have, but of course, what I always did, I always adjusted for the intercept. Okay, so this was the span. This was 1, or the span of 1 over here, and so then I had this forward triangle. Okay, so the regression sum of squares is this square length of that side over there, sitting in front of the board here. Here's y hat, and then I had these sides: SST, SSRes, SSR. Okay. And this, but this is always just E, this vector, okay? From the projection in Rn onto the column space of X to the head of that projection to the head of the projection, excuse me, to the head of Y, okay? That's the error vector, all right? The error vector was just all those little vertical displacements in the cloud picture. All the little vertical displacements in the cloud picture. That is envisioned as this normal to the column space of X. Okay, in this picture. So there's two different pictures: the cloud and this. Okay, where there's no cloud, it's just straight lines. Okay. All right. So you've got this is SSRes. So in the end, I'm going to want to. This is a sum of the EI squareds. I goes from 1 to n, and that related to my sigma hat squared before. I just divided by a certain thing and it gave me my sigma hat squared. I divided by its dimension. What's the dimension of this? Well, there are n dimensions. There's k plus 1 dimensions here. So therefore, there's n minus p or n minus k minus 1 dimensions here. So this should be n minus p degrees of freedom. It should be. Okay? It was n minus 2 in the case of simple linear regression. It's n minus 3 in case of 2 regressors, and n minus p in the case of k regressors, where p equals k plus 1. Okay? So that should be the dimension that E lies in here. Okay, the orthogonal complement of this column space is that dimension. So I've got all this. What's the covariance of E then? Well, I just had this formula. It's I minus h, covariance of y, which is sigma squared, times I minus h prime. But h is symmetric. It was obvious. It's obvious if you go back to it. The x prime x inverse, you know, the x prime x inverse x prime checked. If you take the transpose, it comes out the same. It's symmetric. So, and I times I is I times h is h. You get I. The sigma squared comes out. You get I minus 2h plus h squared. H squared is h. So it comes out I minus h again. So this is I minus h sigma squared. Okay, now I can calculate the expectation of SSR. Expectation of SSR, excuse me, SSRes, which is the expectation of the summation of the EI squareds. Let's see. That's the summation of the expectation of EI squared. The expectation of EI squared is, well, that's the variance of EI squared plus the expectation of EI, the quantity squared. That's the little formula for the expectation of a square, bringing the variance. Now, but what is the expectation of E? The expectation of E, I have a little room over here. Can I do that? Expectation of E. Let's see, wasn't that 0 before?
Yeah.
I think it should still be 0. That's expectation of I minus h. I know this is a lot of calculation, but you can sort of do it on your own. I minus hy. Again, I use my little handy-dandy formulas. That's I minus h times the expectation of y, which is x beta. So this is x beta. What is h times x beta? H is x prime x inverse, x prime, and then I have an x and a beta, so it's x beta minus x beta. So the expectation of E as a vector is the 0 vector, n by 1. Okay? So that means the expectation of every EI is 0. So this is 0 for every I. Coming back over here. So we have E equals E1 through, okay, it's just kind of all the formulas are just falling out now. The variance of EI is the sum of the diagonal elements of the variance covariance matrix. So this is the trace of the covariance of E. The covariance of E we calculated over there is I minus H sigma squared. We calculated the trace of H is P with the K plus 1. All right? And the this is IN. This is an n by n matrix. This H is n by n, but its trace is P. So I get P, n minus P, sigma squared. Sigma squared coming out as a scaling factor. IN means IN by n. Okay? So that's the right thing. And P equals 2, which is exactly the result we had before. It's just a slightly different calculation now. All right? A little bit more streamlined.
So how does this get us our estimator?
Well, that means sigma hat squared is SS res divided by n minus P. That's exactly what we have in the picture on Excel. Did you get it copied? Okay. This is the last thing. Look in here. For the multiple regression, this is problem 3.5, where we take the gasoline mileage data, and now we're taking the number of carburetors besides the engine size. So there are two regressors. There are 2 degrees of freedom for the residual sum of squares, which was this thing down here. Because now the plane, this dimension of the column space of x is 3, but one of the dimensions is taken up by just the intercept. So there's 2 dimensions left here. I'm taking the orthogonal projection here onto this line too. All right? So there's a right angle there. Okay, in the plane. Okay, there's a right angle here that as many right angles as you want. Okay? There's a right angle here. And of course this is a right angle too. Because I'm projecting y onto the line as well. Y bar times 1. Okay, so SSR, that has 2 degrees of freedom. This one has n minus p degrees of freedom, and that's exactly what I divide by. What I'm checking is that n minus p degrees of freedom was exactly the right thing to divide by. This is SS res divided by 29, and you get the 9.077. So you're taking this number and you're dividing it by 29. N minus p in that case is 32 minus 3. 32 minus 3, so that's the 29. All right? 32 minus 1 for the total degrees of freedom, n minus 1. 2 because there are 2 regressors. That's k. So you've got the p is 1 plus k. All right? You get, okay, under, let's see, under the normality assumptions, these are sample values of independent random variables. Under the null hypothesis that both betas are equal to 0, both beta 1 equal to 0 and beta 2 equal to 0, that's unbiased for sigma squared, that's unbiased for sigma squared, and the ratio is actually an F ratio, okay, under the null hypothesis. You got F, so the regression was significant. Again, it had to be already. The residual sum of squares when you add more regressors has to go down. You're getting, before I had a smaller column space, and I was projecting on, now I've got a larger column space. This distance gets smaller. So the residual sum of squares has to get smaller. You can check that. What was the residual sum of squares in the gasoline? That was the very first problem. Residual sum of squares was 282. Now it's down to 263. It doesn't mean that the mean square is going to be smaller, though it is, in fact, in this one. The mean square went from 9.4 to 9.077. Okay? Of course, that was the sigma hat squared. The actual sigma hat is now 3. Okay? All right. So that's the constructing the analysis of variance table. And finding the variances for Well, on your Maple worksheet, you can see, let's go to the Maple worksheet. You have, there's the x prime x inverse for the delivery time data, different data. This is the example 3.1. And so on that one, you're getting something else. So, and you could probably see it up here too. Let's see if we can relate this x prime x inverse matrix that we calculated here that Shane helped us with.
Hey, Dr. Morrow?
Yeah, are we done?
It's 1:35.
Okay, I guess we better quit. Anyway, we'll relate this x prime x inverse matrix that Shane gave us with